Hello everyone, this is Professor Ma and this is the sections on matrix LE. From last sections we introduced the notations of matrices in solving system equations, and in these sections we will do the operations of matrices as subtract multiply. Well, the first thing we want to talk about is the size and positions of the entries in the matrix move per size. And so we have two letters. The R is always refers to rows. So whenever you see capital R, it's row, stands for row, and capital C stands for column. And in particular, we use that interchangeably that if there are rows and C columns, then the size of matrix is R by C. So here's 3 rows, 1, 2, 3, and there are 4 columns. So it's a 3 by 4. 3, oops, wrong colors. 3 rows for the rows and 4 colors for the 4 columns. And so here's 1 by 3, 1 row, 3 columns, and here's a 3 by 1, 3 rows. 1 column. And positions, to access particular, we want to talk about particular row with this row 3, and here is column 2. And the place where intersections, that positions, we call that the entry 3, 2. So the third row, second column entry. And in general, we can think of this, the up as a stage. These are the seats, the entries positions are the seats in your theaters, and the stage is upper head, on top of the matrix, and the seat 3, 2 means here's the door, here's the entrance, you come in, you go to row 3, you go, excuse me, and then you go to row 3, C2. That's the entry 3, 2. So that's how we label the position of the entries. And this is the general positions of R by C matrix, and all the entries are indexed by the seats positions, 1, 1, 1, 2, 1, 3, etc., etc. And what's in general, what's the position Aij? The I stands for the ith row, and the J stands for the jth column. When we add subtract matrix, we require them to be the same size. So here I got the 3 rows of 3 by 2 matrices. I add subtract them entry by entry. So 3 minus 4 is minus 1, and 0 minus 2 is 2, and so on and so on. As the size are different, I cannot add them, so they are undefined. These two are undefined. And now let's talk about multiplication. There are a couple of types of multiplication for matrices. The first type is just rescale the size of the matrix. You multiply every entry by a fixed number. We call that the scalar multiplications, and we denote it by k times a. So for example, 3 times matrix is over here, and you multiply every entry by 3. And this is called scalar multiplications. But the most important operation is the matrix multiplication operations. And this is defined in the following manner. First, we don't define them to be like the way we did for add and subtract, but multiplying entries, corresponding entry, but rather we have this format. We have to have a row matrix, and the numbers of entries in the row on the left is the same as the entry in the columns on the right. And it has to be in this format. And how do we do it? When you have the same, when the size match, you multiply them entry by entry. the row entries times the column entries and pair them up, multiply them. After you finish multiplying them, you add them together. Then what you wind up is a number. It's a one-by-one matrix, only consists of single number. You cannot multiply these two matrices because the numbers of entry in a row versus the number entry in a column doesn't match because you need you need two entries in the column to match the two entries in the row on the left hand. So this is undefined. Okay, remember, it has to be like this. And you can also do this one, as you will see, when we generalize how we multiply matrix in general. And stuff like that doesn't make sense. Undefined. And here's a motivation why we want to define the matrix multiplication in that manner. So for instance, okay, apple costs $20, I want to order 2 pounds, and banana costs $10 a pound, I want 3 pounds. I just write those two information at the bottom. AB stands for how many pounds of apples and banana. And then I can write my cost, the price, $20 for apples and $10 for the banana in a column matrix. And when I multiply them, what's the result I get? I get the total cost for buying both. And suppose tomorrow the price change. Suppose tomorrow the price change to $15 for the apple and $12 for the banana. Then when I multiply these two matrices on the right, then I get the two costs, the cost for the first day and the cost for the second day. So in this way, I can keep tracks of the total cost. Okay, so this is one motivations for why we multiply these numbers. So during this particular example, I have 3 entries in a row, 3 entries in a column. Hence, I can multiply these two matrices. And we proceed like the following. Multiply the first row, multiply the row to the first column, add them. Multiply the first row to the second column, entry by entry, add them. And wind up with the matrix -3, 0. This is a 1x2 matrix. And here is a matrix for the left-hand side, 2 rows. So I do the above procedure twice. First row comes to 2 columns, then go down the bottom row comes to 2 columns. And then I wind up with their product. Okay. So in general, this is the size. How we multiply these. In general, the number of columns, how many seats in a row, has to be equal to how many rows in a column. So the K and the K have to match up over here. These two numbers has to be the same, K and K. And when I multiply these two entries, I get the ith row jth columns of the product. And that is, you multiply the first entry A1, the first entry of A times first entry B, and so on, so on, so on, and add them up. That gives the entry, the ijth entry of the product. In particular, the size of the finished size is R times N. It's R by N matrix. Okay. Oops, it's too fast. And here's examples, and you get to practice, see if things can be done or cannot be done. Okay, so you can read this. Square matrix. Any 2x2 square matrix can multiply into any 2x2. So square matrix can multiply amongst each other without any problem. 2x2 multiply to 2x2, 3x3 multiply to 3x3, 4x4 multiply to 4x4. Okay. And in this multiplication, the diagonal matrix with everything down, 1 down the diagonal and 0 everywhere else. If I multiply any n by n matrix to this matrix, this actually works like the number 1 in multiplications. In other words, I multiply any matrix to this identity matrix, I get back the matrix itself. Okay, the 2 by 2 matrix multiplied by the 2 by 2 identity, I get back the matrix. You can check this. You can check this with 3 by 3 matrices times the 3 by 3 identity. They place the row of the number 1 for multiplication for numbers. And similarly, if I put the number k down the diagonal, 0 everywhere else, and then multiplying any matrix by this matrix is like multiplying by the scalar k. So for example, if I multiply the scalar matrix 3 to A, B, C, D, I get 3A, 3B, 3C, 3D. It works just like the scalars multiplying by 3. That's why we call these matrices the scalar matrices. And here are some basic law of matrices. It's associative. If I have 3 matrices, it doesn't matter which 2 I multiply first. This is not trivial, not easy to show. Okay. And there's have the distributive property of the scalar. Here's a case of scalar. Okay, I can distribute the scalar by multiply matrix. Even if I have a matrix here, the C is a matrix. I can distribute matrix. If everything is defined. One big no-no. A times B is not B times A anymore for matrices. We lost this we call this commutativity. So in other words, matrix multiplication is not commutative. You can easily check. So that's the case. That means all the old algebra rules are not valid anymore. Or you say, why not? Like look at this one. A plus B times A minus B. If I were to FOIL, I will get A times A is A squared plus minus AB minus A times B plus, I'm taking the B now, multiplying to plus B times A, B A minus B squared, B times B. And for numbers, AB and BA are the same thing. So I can cancel. Here, no. We don't have AB and BA to be the same. So in general, it is not true. Hence, AB times B minus A plus B times A minus B is this product. It's A squared minus AB minus B for matrices in general. Okay, do the homework and see you next time. Bye-bye. Stop here. And bye-bye.